Thank you. People can hear me? Okay. So first I'm going to define the two things in the title of the slide of the talk. So sketching. You imagine that you have some data, a lot of data, and you have some function f. And what you want to do is you want to compress the data into some compressed representation, which I'm calling the sketch. And from this compressed representation, you should be able to compute f of the data. So as I've said it, one trivial solution is just the sketch is the function on the data itself. But you might want some other properties of your sketch besides just that. And one property that I care about is streaming. And the picture you should have in mind is you're a router, and there's a lot of data that's streaming at you, for example, packets. And I want to maintain this compressed representation of the data on the fly as I see more and more data. So the router sees more and more packets. And then at the end of the day, AT&T or whoever owns the router says, give me such and such function of the packet data you saw today. Okay? So how can I maintain such a compressed representation on the fly? And the model that we're going to be working with in this talk is the following, what's called a turnstile model. So you imagine you have a d-dimensional vector x. And you should think of d as being really large, maybe the number of IP addresses or the number of pairs of IP addresses, source-destination pairs. And x starts off as the 0 vector. And I see a sequence of updates, I comma v, and each update means add some amount to some entry of the vector x. And our goal is to maintain some sketch of x under these streaming updates, such that at the end of the day, I can compute the function of x just from the sketch that's in memory. Okay? And I don't want to store x explicitly in memory, because that's expensive. Maybe I don't have enough memory to store this huge dimensional vector. Okay, so just so we're on the same page. So here's my router. Here's my 2 to the 32 dimensional vector, because that's the number of IP addresses in IPv4. And I see packets. That's going to destination 3. Maybe I interpret that as increment x3. I see a packet to destination 2, increment x2, and I see a sequence of packets. And at the end of the day, someone asks me how many distinct IPs receive traffic, which is some function of the vector, the support size of the vector. Okay? And I should be able to answer this question and other such questions without actually storing this 2 to the 32 dimensional vector in memory. So what I want to do in this talk is first, I guess a lot of the audience is maybe not in computer science. I just want to give some introduction to this area and show you that there are some interesting non-trivial things you can do. And then before I get into specifically some problems that I'm currently interested in, because I don't want to get, a nice introduction would be good, I think. Yeah. OK, so the distinct elements problem. So that's the problem that I just showed you on the last slide with the router. What's the number of distinct IP addresses that I saw in the stream? Okay, so I have a sequence of integers. There could be repetition. And each integer is between 1 and d. And at the end of the day, someone asks me how many distinct integers are in this list. Okay, so that's the problem. So there are two straightforward solutions. One is I keep a length d vector in memory, initialized to all zeros. And then if I see I in the stream, I flip yi to 1. Okay? So then at the end of the day, I look at how many yi's are set to 1, and that's the number of distinct elements I saw. That takes d bits of space. Another thing I could do is to store the whole list or the whole stream in memory. And well, let's say the list length is m. So there are m stream elements. Each one is a number between 1 and d. That's m times log base 2 of d bits. Okay, so these are two straightforward solutions, and they require memory that's either linear in the universe size d or in the stream length m. Okay, and the question is, is it even reasonable to hope to do much better than that? I want to convince you that there are some non-trivial algorithms that you can apply to this problem. And the basic idea is the following. So if I pick a random number in the interval from 0 to 1, I expect it to be a half. Okay? So how do I use that? Well, how about if I pick t random numbers independently in the interval from 0 to 1? What do I expect the smallest of the numbers to be? Well, this is just some basic order statistics. I sort of expect a picture like this, where those t random numbers are evenly spaced, and the smallest will be 1 over t plus 1. Okay? So what does this have to do with the problem that I just told you? Well, here's an idealized algorithm. Imagine that I had a random function h, that when it sees an integer I, it spits out hi being a random number between 0 and 1 in the continuous interval 0 to 1. And I'm going to record in memory. So what's my algorithm going to record in memory? It's going to record the smallest h of I value I've ever seen over all the i's in the list. Okay? And so what's the idea behind why this works? Well, let's let t be the answer, the number of distinct integers in the stream. So what am I actually seeing? I'm seeing h of I for t different values of I, the t different values of I that are in the stream, and then I expect that to be 1 over t plus 1, and then when I invert and subtract 1, I expect, hopefully that'll be t. Of course, this is very idealized. How do you store such a random function h? It has d random numbers that are involved. How do you store this real number in the range 0 to 1? My computer has finite precision. And we expect x to be 1 over t plus 1, but it won't exactly be what we expect. But you can get around all these issues, and I'm not going to go into it. So you just need an h that's random enough. And in computer science, we have this area called pseudo randomness, where we figure out how to design hash functions or functions h that look random enough. And you can prove that even if you run some version of this algorithm with bounded precision, it'll still work. And you can show that this random variable is concentrated enough that you'll get something that's decent. Okay, so I don't want to go too much. So this is one way to solve this problem. There are actually more advanced ways that use even less memory and get high probability. I don't want to go into all of that. But just to give you a flavor of an introductory algorithm. So here are a few streaming problems, just to show you the kinds of things that people can do or that people have looked at. So the distinct elements problem is what I just showed you. So the desired output is the number of the support size of the vector x. How many entries of x are non-zero? Norm estimation. Maybe I want to estimate the norm of the vector x after some streaming updates, or some empirical properties, some properties of the empirical distribution. If you look at x as defining some empirical distribution, entropy, for example. And then there are some other problems where I don't just want a number as my output. I want my sketch itself to have some property. So for example, oh, good, OK. For example, here, my sketch y itself should be some vector whose norm is very close to the norm of the original vector. Okay? And then y should be really low dimensional, so it fits in memory. Compressed sensing is another thing that's related. So imagine that I have some promise that x is going to be approximately sparse after I stream the vector. And now what do I mean by approximately sparse? I mean maybe it's a sparse vector plus some noise. And I want to recover a vector x tilde such that x tilde is close to x under some norm. Another one is linear regression. So here, let's say the matrix A is being streamed over. So imagine I'm Netflix. I have this matrix where I have users on the rows and movies on the columns. And the ijth entry is how did user I rate movie J after he saw the movie. So this is a matrix that's getting streamed over, because as time goes on, people are watching more and more movies. They're rating more and more movies. And I want to be able to solve some numerical linear algebra problems to this dynamic matrix, for this dynamic matrix. And another one that people care about is also low rank approximation. I want to find the low rank matrix A tilde that approximates A as closely as possible under some norm. Here I put Frobenius norm, but really, people care about other norms as well. And I'm also going to be focused on randomized algorithms and approximate algorithms for the following reason. So there's this work which it wasn't the first streaming paper, but it was kind of the one that really brought a lot of life into the field, that said that for a lot of these problems, well, they really only focused on a couple of these, but their arguments extend to a lot of problems as well. If you want to have a solution that gets sublinear space, meaning your space is not linear in the length of the stream or the size or the dimensionality of the input, you need to settle for some kind of slack in two ways. First of all, you can't hope to get an exact answer to your problem, just some answer that's some good approximation. So for example, with the distinct elements problem, I won't know exactly how many IPs receive traffic, but I'll know the answer to within 1%. And also, there's some non-zero probability. I'll have a randomized algorithm, and my randomized algorithm will have the property that it outputs some bogus answer with some small probability. Okay? And the smaller you want to make that probability, your memory will increase. And for the remainder of the talk, I'm just going to focus on these three things, which are things that I've been looking at a lot lately, and mention some open problems at the end. So the dimensionality reduction, as well as compressed sensing and linear regression. Okay, so any questions so far? I guess I have. OK. So here's one kind of dimensionality reduction theorem due to Johnson on Lindenstrauss. So here's the goal. I want to find a distribution. There's no S here. I want to find a distribution over linear mappings from d dimensions down to m, such that if I have any fixed vector x, a random matrix from this distribution will preserve its norm with high probability. So this probability is over S, and it's for all x. So for all x, the probability over S that x's norm is preserved after applying S is at least 1 minus delta. And what Johnson and Strauss showed is that if you choose enough rows in this matrix S, so a number of rows that's even independent of the original dimension, this is possible. Okay? And for example, you could project to a random subspace or pick a random Gaussian matrix. There are many different constructions of this. And it has several applications. I'm not going to get into them, but there's even a whole book in computer science on applications of this lemma. And a corollary of this lemma is the following, or of this theorem is the following. For any set of n vectors in Rd, so x1 up to xn, there exists some matrix S which depends on these vectors, such that for all pairs of vectors xi and xj, the L2 distance after applying S is preserved up to 1 plus epsilon. So S preserves the geometry of the vectors x, at least with respect to the L2 norm. Okay? And you can set m to be logarithmic in the number of points n, again, independent of the dimension d. And this follows from this theorem by basically just setting this d to be 1 over n squared, and then union bounding over the set of all difference vectors. Okay? So what are some, as computer scientists, there are certain things we care about. We care about some computational issues concerning this theorem, this Johnson-Lindenstrauss projection. A few of them, for example, are minimize the number of random bits it takes to pick a matrix S. Okay, so I said a random matrix, a random Gaussian matrix works, but can we come up with constructions that need very few random bits? We want to calculate Sx quickly. So I want an S that's somehow efficient to apply. More efficient than just some naive matrix vector multiplication. Another thing I care about, especially in streaming, is I want S to have very good column sparsity, meaning that every column should have very few non-zeros. Because if I'm doing streaming updates, remember, in a streaming update, I add some amount to some coordinate of x. Let's say I add v to x sub I. What that means for updating my sketch is I should add v times the ith column of S to my sketch. Okay? And if there are very few non-zeros per column, that means I can do that quickly. So what are some things we know about the kinds of S that work? So the original proofs basically took a random dense matrix, random signs, random Gaussian, et cetera. I guess this is actually, I don't know why I put 10. It's really 12. So in some joint work with Daniel Kane, we showed that actually you can get matrices that are much sparser. Only an epsilon fraction of each column is non-zero for the same m. On the other, and then there's the structured matrix approach where you basically use samples from the Fourier matrix, random samples from the Fourier matrix. And you can get one of two different kinds of results there. It's known how to get something like d log m embedding time. Oh, by the way, so here x0 is the number of non-zero entries in the vector x. Okay, so basically what this says is I'm going to take a random dense matrix. So there are m non-zeros per column. So I can multiply an m times x0. Here it's saying there are only epsilon m non-zeros per column, so I can multiply faster. And these structured approaches, using FFT, I can get fast multiplication. But the running time doesn't depend on sparsity of the input. OK. And I said I was going to talk about 3 problems, namely compressed sensing and regression, et cetera. And I'm just going to sketch in this one slide some connections. Basically, these are almost the same problem. I'm going to convince you of that. Or not the same problem, but JL implies things about these other problems. So compressed sensing, I don't have time to really explain why this is a good error bound to hope for. There are other things you could hope to put on the right-hand side, but under some, basically, this is, in some sense, this is one of the strongest things you can get. That you can, there are stronger things you can provably not get. So from my sketch S times X, I want to recover, remember S has very few rows. So from this very small sketch, I want to recover some vector x tilde that's close to x. And how close is it to x? Basically, the distance should be at most the norm of the tail of x. So this inf over k sparse z is basically set z to agree with x on the heaviest coordinates of x. So this is proportional to the norm of the tail of x. Okay? So if x is a sparse vector, if it's a k sparse vector, this error term on the right-hand side is 0. If it's close to sparse, then this is small. And it's known that it suffices for S to be some what's called an OurIP matrix for this to work. And what's an OurIP matrix? This looks a lot like JL. OurIP just means S preserves the norms of all sparse vectors. And how about regression? So regression says I have this matrix A and I have a vector B, and I want to compute an x which minimizes. So let's say I have this linear system. Okay. Normally, hopefully I could solve this linear system and then just have ax equals b, and this distance would be 0. But maybe this linear system doesn't have a solution. It's over-constrained and there's no solution. I want to find an x which minimizes, which is as close to a solution as possible under this norm. Okay. So Sarlosh had this observation in 06 that really it suffices to just minimize SAX minus SB, where S is some dimensionality reducing map. And S just needs to preserve the norms of all vectors in the subspace spanned by B in columns of A. This is it's a simple observation. Okay. And again, that's a very JL-sounding statement, right? You want to preserve the norms of a set of vectors. And in fact, really, JL implies the existence of maps for both of these problems. For OurIP, you can just do the JL theorem on some net of the sparse vectors. And for regression, you can do JL on some net of a low-dimensional subspace. Okay, so what are the open problems? Now I have just one last slide. And I want to state what are the open problems that I'm interested in that connect JL to compressed sensing to linear regression and some more generic JL kinds of things. So here are two concrete open problems. It's known that, so one is how do you come up with these OurIP matrices? By the way, so from this line here, I said basically JL implies OurIP because you can do JL on a set of sparse vectors. There's also some kind of inverse theorem as well by Kramer and Ward. So, you can improve JL also by improving OurIP. It's known that if you sample some number of rows from the Fourier matrix, you get OurIP. And the number of rows you need to sample, currently it's not known how small you can make that. The question is, can we get something that's known to be optimal for sampling rows from the Fourier matrix? Also, this is sampling random rows from the Fourier matrix. So a set of random rows works. That implies that there is some set of fixed rows that works. What are they? So can we figure out which rows to use and come up with an explicit OurIP matrix? And the first question, by some analysis of Rudolphson and Verschinen, it really boils down to understanding some fixed expression involving soups of Gaussian processes. Okay, and basically omega is a random set of Fourier rows. If you can understand the expectation of the soup of g dot x, where g is a random Gaussian vector, where t is this set, then you could hope to really prove this theorem. Okay, there's some path to proving this theorem. And the second open problem before I leave is understand the sparsity that's required in JL in terms of the geometry of the point set. So the theorems that we have now say something like, for all sets of n vectors x1 up to xn, there is a matrix S with this number of rows and this sparsity that works for these xi's. But if you have some additional knowledge about the geometry of your vectors, you can hope to get away with fewer rows and with much better sparsity. And in fact, there's a theorem by Klartag and Mendelsohn which shows that you can get away with, so this is some expression that involves the geometry of the vectors xi minus xj. You can get away with some number of rows if you just choose S to be a random Gaussian matrix with that number of rows. And by the way, this is never bigger than log n. So it's never bigger than log n over epsilon squared, which you get from the generic JL. But if your vectors have some nice geometry, you can get away with much less, even a constant sometimes. And what I'm interested in is how sparse can we make the matrix S depending on the geometry of the point set. And there are no theorems that go along these lines. So we have theorems recently me and some colleagues were able to prove some theorems of the following kind. OurIP matrices must be dense. Also, if you want to preserve a subspace, you can actually be very sparse. So what is it about the net of a low-dimensional subspace which lets you get away with sparse matrix S? And what is it about the net of sparse vectors which makes you not able to get away with sparse matrices? Okay, so I want to understand sparsity in terms of the geometry of the point set. And that's all.